Hi everyone, my name is Arya Rao and I'm the director of the Science Squad. And for today's edition of the lecture series, we have Dr. Trouba from Ferris State University coming to lecture about ballistics and mathematics today. So thank you so much to him for coming on, and I'll just let him take over.
Am I on now?
Yeah, you're on. Yeah, you're on.
Okay, good deal. Well, welcome everybody. Thank you, Arya, for the invitation. I'm broadcasting live from my basement, so the beautiful wood paneling behind me. I'm Jerome Trouba, as Arya said, and I teach mathematical modeling at Ferris State University. So tomorrow, in fact, on the last hot day of the summer, we're going to launch water rockets. So it's a 2-liter bottle, and it contains a mixture of air and water, and you pressurize it, and then you release it and it shoots it up into the air. And so our kind of goal for this project is the best mix of water and air. How much water do you have in the 2-liter? And then the more water you have, the heavier it is, but the more exhaust of water you have. Anyway, so you're trying to get for maybe max height, because that's the most exciting. So let me show you what I'm talking about. I thought about broadcasting live outside, but I think it'd be a little hard to see the rocket. So here's a video from last time I did this. Oh, you know what? To technology. I need to switch. Hold on a second. There we go. Last time you'll see me. Okay, once again, here's the video of the last time I did this. Yes, I did not play football. Okay, so what you can see from that, I'm going to go back to Google Hangouts. Okay, yep, it's working. All right, just wanted to make sure. I just want to show you this one more time. I'll pause every once in a while here. So, first of all, when it's going up, you can see that it's straight up. And again, it's not too high, it's not very exciting. Now notice when it comes down, it's sideways. And this is going to be important later. Okay, and then there's me missing. Everybody gets to laugh. Okay. So, what I did with this is I collected data. And the first data, this is really not too exciting, but I like to clarify graphs. So I'm going to show you this particular, whoops, not these graphs. Those are what I'm going to show you, just in case I forget. All right, and Desmos is my magical program, and really this is what's going on. The rocket goes up. I don't have time here. I'm just talking about rocket going straight up, spending a lot of time at the top, and then coming down again. But as you can see, that's really not very exciting. Nothing's really happening. So what we do is we incorporate time into it. So here's the 90-gram rocket. So this rocket has no water in it. It's as boring as it comes, but it's a good starting bit. So what I did is I recorded data every 10th of a second, and then its corresponding height. So I actually had a ruler on my computer screen taped to it, and I got the height for 3.8 total seconds. So let me show that to you here. So let's just go new graph. Okay, and paste that data in. Okay, now that's looking a lot better. And let me adjust this a little bit so we can get a little better view. Okay, so as I like to tell students, this is not the path of the rocket. You clearly saw the path of the rocket. It was just up and down. But what this tells us, at 2 seconds, the rocket was at about 32 feet. Okay, and then it hit the ground at about 3.8, 3.9 seconds. And that's not the path, but it's just time, height. Okay, so what we can do with this is some pretty cool stuff. Kinematics is the study of the motion of objects. And so one of the kinematics equations, which you might know from physics if you have physics, is this one right here. And so I have the height as a function of time, and that's equal to 1/2 the acceleration due to gravity. Usually this is negative, usually negative 32. The time squared, plus the initial velocity times the time, plus the height. So this is a quadratic equation. It makes parabolas. In our case, we have no initial height because our rocket started at the ground. Just start over here again. And there we go. Rockets are the ground, so the initial height is going to be 0 for us. Okay, so let's go in, and I got to minimize this. There we go. Okay, let's go in, and we can use Desmos to kind of try to fit something to this. So this is model fitting. So I'm going to use something called regression, and it's this little tilde key. So I need to actually say y1, and then I'm going to say it's going to fit a function. So I'm going to say acceleration due to gravity, x1, that's going to be squared, and then I'm going to do plus velocity times x1. And my initial height is 0. So if I do this, I have this nice parabola, okay? So it's just ax squared plus vx1 here. We just have a parabola, right? Opening downward. And as you can see, it's kind of shifted a little bit off from the maximum. What regression is trying to do is maximize this r squared value. And what it's doing is it's trying to get as close to all the points as possible while still being a parabola. So as you can see right here, we're a little bit under the points, and over here we're over. So the program's trying to balance between the two of them. So it does an okay job. But I think we can do even better. So let's take that one off. Well, we'll leave it on just for a moment. So I'm going to say, let's let y equal. And I want to do a parabola, but I'm going to do a parabola where I know the vertex. So back up to my data points. Let's see. There's 1.5, 33.3. That's right here, the vertex, the very highest point at 1.5 seconds. So I'm going to use that. Try to fit a better parabola. Now, what does it mean by better? I don't know. You're going to see what I'm talking about. Okay, so there's my parabola. I'm going to get rid of the blue one, and we're going to have the black one. Now, I have A. Oh, so I'm sorry. I don't want to use A. Let's use B. Okay, we can put a slider in here. And, yeah, that's no good. So we need to alternate. We need to adjust B. So let's see, negative 20 to 20. Okay. So let's adjust it. Right, so we're just a parabola. And I'm trying to right now adjust for the left side right here. Kind of the best job I can do on the left. And so I'm trying to get a pretty good adjustment. And yeah, I'd say about negative 15 is doing a pretty good job all the way up to the vertex. Not so much over here, but all the way up there. Now, let me talk about this just for a second, this negative 15. If we go back to this equation, 1/2 times the acceleration due to gravity. As I said, that's normally negative 32 feet per second. So 1/2 of that's about negative 16 feet per second. So as you can see right here, I'm about pretty close to that negative 16 mark. I'm at negative 15. All right, so it does a pretty good job, this regular old parabola, of capturing what's going on. Now, if we look at the back side, okay, now I have to adjust it more, and yeah, it's not so good. It's a little harder to do it on the back. Well, the problem is, when the 2-liter bottle is falling, we have air resistance, a lot more air resistance. I'll show you that video again. Whoops. There we go. All right. And, oops, too far. Okay, try again. There. Apparently this is harder than I thought. Oh, there you go. Oh, yeah, right? It's falling sideways. There's a lot more surface area, a lot more air resistance, and it falls a lot slower. Okay, now if you have a ball, that's a little bit different, but this was a different object, like a 2-liter. So